Weather. If you understand the weather, you own the weather. Many people complain about the weather, but a rainy day takes on a different complexion if you predicted that it would rain that day. That it rains when you said it would becomes a matter of pride rather than misery. You see, if you have a fine sunny day, you have cold air falling and higher pressure. And if you have a cloudy, rainy day, you have warm air rising and lower pressure. Those are the fundamentals of our weather. And from where I'm sitting in England, I can add that on sunny days with higher pressure, the wind will be lighter and will come from the northern half of the compass. And on rainy, cloudy days, the wind will be stronger and will come from the southern half of the compass. All we have to do is work out when we will have a fine sunny day with lighter winds and when we will have a cloudy, rainy day with stronger winds, and why. You see, weather is all about heat, and the heat comes from the sun. The sun warms the ground, which warms the air above it, and this air rises. As it does so, it takes weight off the ground, creating low pressure. The space where the warm air had been is then filled by cold air. This cold air has been falling and has added its weight to the ground, causing high pressure. It, in turn, will be warmed and will rise, and so the cycle continues. Our atmosphere, or the bit we get most of our weather from, which is called the troposphere, gets cooler the higher you go. So warmed air rising will start to cool as it rises, and water vapour within the air will condense out as cloud. If it cools further to what we call the dew point, this cloud will produce rain. This is why you see fluffy cumulus clouds at the end of a warm summer's day, and why you occasionally get a quick light shower that seems to come out of nowhere. Notice, too, how it gets chilly when the sun goes down on a clear summer's day. That's because our clear air is caused by cold air falling, which creates higher pressure. The sun goes down, the heat goes out of the ground, and we feel the chill of the cold air. The cooling as the air rises through the atmosphere is referred to as the lapse rate, or more accurately, as the adiabatic lapse rate. And this differs between dry air and moist air. Dry air cools at the rate of 10 degrees centigrade for every 1,000 metres it rises, and this is called the dry adiabatic lapse rate. Moist or saturated air, as it's known, cools by 5.5 degrees centigrade for every 1,000 metres it rises, and this is called the saturated adiabatic lapse rate. You can tell if the air is dry or moist by looking at jets overhead. If they leave a contrail, the air is moist. It has water in it. And if they don't, it's dry. And this rising and falling of air and pressure differences is what causes wind. Now, wind wants to blow from high pressure to low pressure. So you might think that with the sun beating down on the equator and heating the air above it, resulting in low pressure, and with cold air falling at the poles and creating high pressure there, that the wind would blow from the poles towards the equator. Only it doesn't, for one reason. Because the Earth is spinning about its axis. At the equator, the Earth is spinning in an easterly direction at about 1,000 miles an hour. Here at 52 degrees north, we're doing about 625 miles an hour. And this spinning causes a twist. It's called the Coriolis effect, which was discovered in 1835 by a French scientist with the grand name of Gaspard Gustave de Coriolis. The spinning Earth causes moving objects on the surface of the Earth to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. So if I stood on the equator and threw a ball north towards London, it would land in Moscow. Here's a demonstration of the Coriolis effect in action. We need first of all to show that when we're stationary on the Earth's surface, it's perfectly possible to throw a ball straight, and that is just what Peter and Hannah, who is directly in front of me and below the camera, are doing. We then persuaded a man at the fairground to allow us onto his cage ride, and we checked again that when stationary, the ball thrown across, this time with Peter in front of me and below the camera, and Hannah on the other side, goes straight. You'll notice Sally standing to the left of Hannah. Leslie, whom we never see, is standing to the left of Peter and me. Now, we spin the cage anti-clockwise, just as the Earth spins anti-clockwise, and try to throw the ball straight across. And it's deflected to the right every time. And that is the Coriolis effect. So winds are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. Remembering that wind wants to blow from high pressure to low pressure, we now find in the northern hemisphere that being deflected to the right, it actually blows in an anti-clockwise direction from high pressure to low pressure. In the southern hemisphere, the opposite applies. But why does the wind blow? It blows because there is a difference in pressure. The greater the difference over a given area, the stronger the wind. And we measure pressure in millibars of mercury. The higher the pressure, the weight of the air on Earth, the greater the number of millibars. Average pressure at sea level is 1,013.25 millibars, which is a sort of zero between high pressure and low pressure. And this is referred to as mean sea level pressure, or MSLP. But wind will blow as long as there is a pressure difference, regardless of whether it's above or below 1,013.25 millibars. Because we want to know where the wind will blow and how hard, so we join up equal points of pressure and create a line, an isobar. Here are some isobars: high pressure in blue, suggesting cold air, on the right, and low pressure in red, suggesting warm air, on the left. I like to think of the gaps between the isobars as stairs with differing size steps or risers. The numbers above the isobars, 1032 down to 984, are the millibars of pressure that each line or isobar represents. The closer together the isobars, the stronger the wind. From 1016 to 1032, the wind will be quite light. Down at the 984 to 1000 millibar end, the wind will be quite strong. So there are our steps, but of course the wind is not blowing straight down because of the Coriolis effect. It is being deflected, to the right in the northern hemisphere and to the left in the southern hemisphere. Now, before we get into weather systems, we need to remember that wind is described as where it is coming from. A north wind will blow from the north. But if this wind were to move clockwise round the compass and to start coming from the northeast, this wind shift would be described as veering. And if the wind shift were to move anti-clockwise round the compass and blow from the northwest, the wind shift would be described as backing. So we have the initial wind, a wind that has veered, and a wind that has backed. Now we're ready to talk about weather systems. We have two types of system, a high-pressure system and a low-pressure system. Remembering what we said about the Coriolis effect and winds blowing from high pressure to low pressure and being deflected to the right, so wind around a low or depression or cyclone, as it's also called, will blow in an anti-clockwise direction in the northern hemisphere. Here we have circular isobars, or lines of equal pressure, and the wind is blowing anti-clockwise. You will notice from the arrows that are showing us the direction of the wind that they're backed a little off the direction of the isobar. Wind is always backed a little off the direction of the isobar because of friction with the ground or sea. Wind blows in towards the centre of a low. With the high, or anticyclone, where high pressure is at the centre, the wind blows outwards. From high pressure again towards low pressure, and this time the wind blows in a clockwise direction in the northern hemisphere. And this is what you get with multiple systems. The wind blows anti-clockwise round the lows or cyclones and clockwise round the highs or anticyclones. Where you have a low and a high next to each other, the wind between the two is strengthened because at that point the clockwise and anti-clockwise winds meet and combine with each other. Where you have two of the same system next to each other, the winds between the two are opposed, and so the strength of the wind is reduced. Notice the area bottom right between several systems where the wind is being cancelled out. This is called a col, and the area will be calm. Here we have an app, Windy, showing us a high-pressure system round the UK where the wind is blowing clockwise, and a low-pressure system centred on Scandinavia where it is blowing anti-clockwise. Notice how where the low and high-pressure systems meet, the wind between the two is strengthened as the winds from the systems blowing in the same direction, a northerly wind, are combined. Where we have two lows together, this one here, and then to the west of it, this one here, the south-southwest wind of this low is cancelled out by the north-northeast wind of this low. And here's a useful tip provided by Bausch Ballot, a Dutchman. We always used to call him Buys Ballot until I had a Dutch girl in the class one time and we discovered that his name was pronounced Bausch Ballot. Who knew? Well, she did. Anyway, he said that with the wind to your back in the northern hemisphere, the low will be on your left. Here, with a north wind to his back, the low will be on his left, to the east, and the high will be on his right, to the west. It's the other way round, of course, in the southern hemisphere. So how does a depression, or low, or cyclone develop? And what sort of weather can we expect during the passage of a depression? In the UK, our weather is created by warm, moist air from the Caribbean, which is full of water vapour, meeting cold air from the North Pole out in the Atlantic. The cold air tries to get under the warm air, and the warm air tries to climb over the cold air, and we have pressure differences, and a depression starts to form. This has a centre around which the wind blows. What you're looking at here is a basic version of a synoptic chart. Synoptic meaning a general summary, a synopsis. Here you can see a profile view of the warm and cold air sectors. The cold air ahead of the warm front, the warm air, and then the cold air of the cold front. And there will be specific and very different weather as the depression passes over us. Each of these letters relates to the weather we will experience. At A, we're having a lovely sunny day. We have high pressure, the sky is clear because we have cold air falling, and there is a light wind. We will see cumulus clouds in the afternoon, where warm moist air has risen, having been warmed by the ground, which has been heated by the sun. The air has risen, and the moisture within it has condensed out as cloud. We notice at A, high up in the sky, some cirrus cloud, wispy cloud, which is being beaten up by a lot of wind. This is our first indication that a depression is on the way. As the depression approaches, so the pressure will drop, and at B we will probably have overcast skies and rain. The wind will increase in strength and may well back. As the warm front goes through at C, so the wind will veer. Pressure in the warm sector D will remain constant. It will be overcast, it may rain, the air will feel warm. Then at E, in front of the cold front, we may encounter the storm cloud cumulonimbus. This can give us everything: strong winds, thunder, lightning, heavy rain, hail, snow, well, the lot, because it's a cauldron of warm air rising in the centre and cold air falling at the sides, like a bonfire on a summer's day. It's the one cloud that planes avoid, and it has a very distinctive anvil shape to it. At the cold front, the wind will veer sharply. The pressure will rise, and the sky will be angry with dark clouds scudding about and squally showers. Then we will spot a little patch of blue up in the sky and know that we are coming out of the other side of the depression. The pressure will continue to rise as we will have cold air falling once more. Eventually the whole sky will be blue, the sun will be shining, the wind will be light, and we will have our lovely sunny day back. Until we spot some cirrus cloud way up in the sky, and we know it's going to happen all over again. Here's a more detailed diagram of what I've just covered. This diagram can be found in my books Stress-Free Sailing, Stress-Free Motorboating, and of course Stress-Free Navigation. Or pause the video here and have a good look at it. This is what will be happening at each stage of the passage of a depression. A quick rundown on clouds. Cirro means high, alto means middle, stratus means layered, nimbus means rain. So we have high clouds from 23,000 to 40,000 feet, cirrus, high and wispy, cirrostratus, high and layered, cirrocumulus, high and fluffy. Middle clouds, 6,500 to 23,000 feet, altostratus, middle and layered, altocumulus, middle and fluffy, nimbostratus, layered and rainy. Low clouds, up to 6,500 feet, stratus, layered, stratocumulus, layered cumulus cloud, and cumulus, fluffy cloud. From the ground all the way up to 40,000 feet, we can have the cumulonimbus cloud, the rainy storm cloud. Now back to the depression. Low-pressure systems develop, mature, and then dissipate. As it develops and the depression moves through, so the cold front catches up the warm front. Warm fronts, which are full of moisture, move more slowly than cold fronts, and when the two fronts come together, this is referred to as an occlusion, an occluded front. What's happening is that the cold air behind the warm front is pushing the warm air into the cold air ahead of the warm front, and the warm air gets squeezed upwards, and as the warm air rises, naturally it cools and condenses out as cloud, and when the dew point is reached, as rain. On a synoptic chart, this is shown with the semicircles and spikes together. The occlusion shows that the depression is dying out. There are two types of occluded front. The cold type, where air behind the warm sector is colder than that ahead, and we experience weather similar to a cold front. And the warm type, where air behind the warm sector is warmer than that ahead, and we experience weather similar to a warm front. Either way, it will probably be raining. There is one other major influence on our weather, and that is the jet stream. Jet streams are ribbons of very strong wind that circle the Earth from west to east at a height of between 20,000 and 50,000 feet. They push air masses around and influence our weather patterns. In essence, when the jet stream is to the north of us, it drags warm Mediterranean air up over us, and we have warmer than average weather. If it is to the south of us, it will drag cold polar air down over us, and we will have colder than average weather. And if it's directly over us, it will increase the severity of any depression as it sucks warm air upwards, resulting in windier, wetter weather. Now, judging if the weather will improve or worsen can be made easier by following the crossed winds rule. You've seen what a depression looks like on a synoptic chart, and that shows you the wind you will experience at ground level. If you then look up high in the sky, you will see the upper clouds, and the direction they're travelling in will give you the wind direction up there. The crossed winds rule tells us that if we stand with our back to the wind, and if the upper clouds or wind come from left to right, then we're in front of the depression, the warm front, and the weather will worsen. If the upper clouds or wind come from right to left, then we're behind the depression, behind the cold front, and the weather will improve. Also, where our wind is coming from dictates the weather we will get. Arctic maritime wind is cold and damp. Polar maritime is cold and wet. Polar continental, cold and dry. Tropical maritime is warm and wet, and tropical continental is hot and dry in the summer and colder but dry in the winter. And wet air will give us more rain. That's it for Weather 1. In Weather 2, we look at the synoptic chart, the weather apps, grid files, local wind effects like sea breezes, land breezes, converging and diverging winds, wind shear, and fog. Let's start with the synoptic chart. This is a simplified version of a synoptic chart. These are the isobars. That's lines of equal pressure. Here we have a warm front marked by the semicircles. Here we have a cold front marked by the spikes. This is a classic depression or cyclone or low. Up here is the centre of the depression, and this depression is heading in an east-north-east direction towards Scandinavia. Most of our depressions head off in the direction of Scandinavia. We can tell which way the depression is heading from the isobars between the warm and cold fronts. Now, we're going to get different weather at different points as the depression passes through. If you remember, at A, we'll have a lovely sunny day. We'll have cold air falling. The sky is clear, the sun is shining, warming the ground and the air above it. And we see up in the sky cirrus clouds. And that tells us that we have a lot of wind up there, and we have a depression on the way. As the warm front comes towards us, so the pressure will start to drop. The wind will strengthen and will start to increase. It'll become more overcast and it'll start to rain. At B, it's raining. Then as the front goes through, it'll continue raining, but you'll notice here that the wind veers slightly. It was coming from southwest and now it's coming from west-southwest, so that's a slight veer. The air will feel warm at sea and the pressure will remain constant, and it will be overcast and probably raining. And then as the cold front comes through, we will meet the storm cloud, the cumulonimbus at D, and we'll start to get squally winds and rain. As the front goes through, so the wind will veer sharply from west-southwest here to northwest. As we move out beyond E towards F, we'll start to see blue in the sky, and at F we'll have a nice sunny day again. Now we can find the wind speed by measuring the distance from one isobar to the next, and then taking it to the scale at the bottom. Scale A is for wind speed. We can also measure the speed with which the fronts are moving. If you measure between the isobars at the warm front and take this to scale C, you get the speed it's moving at. And you can do the same with the cold front using scale B. The wind direction does not follow the line of the isobar exactly, but is backed off it by about 30 degrees, like the red line here and the red lines here. This weather map shows the sea areas, North Utsira, South Utsira, and so forth. And you can see here Fitzroy. This is named after Admiral Fitzroy, who put the sea areas together and created the Met Office. The area used to be called Finisterre, but was renamed in honour of him. OK, now we're looking at the real thing, and it's a good deal more complicated than the synoptic chart we were looking at earlier. You've still got your fronts. There's the warm front, and there's the cold front. Right behind it is a warm front that's been caught up by a cold front and become occluded. And we can see from the symbol on the chart that it is filling, meaning it is disappearing. Fronts can remain as they are, but if the relative temperature differences between the warm air and the cold air increase, the front will deepen, and conditions will become worse. And if the relative temperatures between the air masses lessen and become more equal, then the front can fill, which means it fades away. So in terms of symbols, remember, cold fronts have spikes. Warm fronts have crescents. Occluded fronts have spikes and crescents together. And then if an occluded front becomes stationary, we have spikes on one side and crescents on the other. Then a front that is filling, in other words dissipating where the weather will improve, we will have a cross between the crescents or spikes. And if it's deepening, in other words the weather will worsen, it has a dot between the crescents or spikes. Back to the synoptic chart. This is the centre of the depression, and the pressure is incredibly low at 956 millibars. You can hardly get a Rizla paper between the isobars here, so the wind strength here is going to be extremely high, somewhere around 80 knots. By comparison, let's measure across between these two isobars. We'll take that up to the scale and mark it off at the 50-degree latitude point, and the wind speed will be about 30 knots. But in fact, this being a geostrophic chart is the wind speed at an altitude of about 1,000 metres, and we need the wind speed at sea level. We've already said that the wind direction will be backed off the isobars by about 30 degrees because of the effect of friction of the wind blowing over the sea. Well, this friction also reduces the wind speed by about 2/3. I find it easier to work out 70% of something rather than 2/3, and so this 30 knots will be about 21 knots, force 5. And that's how we measure wind speed on a geostrophic chart. We measure across the two isobars and take the measurement up to our latitude on the scale and read off the wind speed and take 70% of it. We don't have here a scale for measuring the speed that the fronts are moving like we did on the other synoptic chart. Incidentally, the pressure figures shown on this geostrophic chart are pressures at sea level and have been converted from the atmospheric pressure at 1,000 metres or so. Remember, mean sea level pressure, or MSLP as we call it, is 1,013.25 millibars. So out here we have a nice sunny day. We see cirrus in the sky, the pressure starts to drop, it starts to rain, the wind strengthens, and as the front goes through, you can see the change in direction of the isobars as the wind veers slightly. And if you find the layout of this chart a bit confusing, it's because it is a gnomonic chart, where the lines of meridian converge from the equator to the poles, as opposed to a Mercator chart, where the lines of meridian are parallel and head due north. Then, as the cold front goes through, the wind veers again. The synoptic chart shows you the centre of the high pressure where the wind blows clockwise, from the centre outwards. You see clockwise around the high pressure, and then anti-clockwise around the low pressure, a figure of 8, if you like. At the centre of the low, because the wind direction is changing so drastically over such a small area, rather than describe the direction for each tiny area, they refer to it as cyclonic, meaning changing a great deal over a small area. Here we have an occluded front, and here we have two fronts that are deepening. The temperature difference between warm air and cold air is increasing. In terms of rain, we can expect it in front of and behind the warm fronts, the cold fronts, and the occluded fronts. It'll be a lovely sunny day out here. Well, that's a good run round the synoptic chart. What you need to do now is to monitor your barometer to see what the pressure is doing, then look at the synoptic chart, then look outside and marry the three things up. Here we have a pressure of 1016 millibar. The synoptic tells us that we have an occluded front overhead, and when we look outside, as expected, it's overcast and drizzling. Perfect. 24 hours later, the pressure has risen from 1016 to 1025. The synoptic shows that we're just behind a weak cold front that's disappearing, and we have high pressure from cold air falling, which indeed we do, as it is a sunny day. Do this, and very quickly you'll become adept at interpreting the synoptic chart. If in doubt, you can always check your phone. Then, of course, we have weather apps. Here we have Predict Wind and then Windy, and they give you a live and projected view of the wind and the weather. They're working to averages, so there is the possibility that they may underread wind speeds. Just bear this in mind. Then we have GRIB files. GRIB stands for Gridded Binary, which in turn stands for General Regularly Distributed Information in Binary Form. It's just a data format used in meteorology. Here we have passage weather GRIB information for weather patterns across the Atlantic. The colours give you the strength of the wind. This is also indicated by the wind arrows. The back of the arrow has barbs which give you the wind strength. Half a barb is 5 knots. A whole barb is 10 knots. Here the arrow is pointing due south with the barb at the northern end of the arrow, and so the wind is from the north, and it has 1 barb, so the wind strength is 10 knots. This wind arrow here shows that the wind is south by west, very nearly coming from due south, and the wind strength is just 5 knots, half a barb. Here we have 40 knots of wind from the west. You can also get barometric pressure and wave heights. Here we have the wind direction and strength round the UK, then the barometric pressure, and then the wave heights. I find it quite useful to see what's coming across the Atlantic, so we know what to expect. Now, local wind effects. Land heats up and cools down much quicker than the sea, which leads to sea breezes and land breezes. Sea breezes are caused by the sun heating up the land, which warms the air above it, which rises, which, with an element of the gradient wind helping it, is pushed out to sea. This air, then having risen, cools and falls. Cool air from the sea goes to fill the gap of the warm air that has risen off the land. This in turn warms and rises and heads out to sea and falls, and very quickly a cycle of cold air falling out at sea and moving towards the land where it will be warmed is created. This wind blowing from the sea to the land is called a sea breeze. When the sun goes down, the earth cools very quickly, and now we find that the temperature of the sea is warmer than that of the land, and so air above the sea is warmed and rises, and its place is filled by the cooler air off the land. The warm sea air, having risen and cooled, falls now on the land, and the cycle of the day is reversed, and we have a land breeze where wind blows from the land out to sea. Temperature differences tend to be greater during the day between the heated land and the surface of the sea than they are at night by the land which has cooled and the surface of the sea, so sea breezes tend to be stronger than land breezes. Converging and diverging winds. Wind blowing over the land and sea experiences friction, which makes it back, meaning the wind direction changes in an anti-clockwise direction, such as from north to northwest. The land causes it to back by about 30 degrees and the sea by about 15 degrees, and this difference means that when sailing near the coast you can experience either a strengthening of the wind over the forecast or a reduction in wind strength. Take a southwesterly wind blowing up the English Channel. At the French coast, the wind over the land, backed by 30 degrees, converges with the wind over the sea, backed by 15 degrees, and it strengthens. Conversely, by the English coast, the wind over the sea is backed by 15 degrees, while the wind over the land is backed by 30 degrees, and as the two are diverging, wind will reduce in strength. So if you're sailing from France on this day, you can expect the wind strength to be stronger by the French coast, less mid-channel, and then even less by the English coast. It's worth keeping an eye on this, especially if you're sailing close to the coast, where you might find that you suddenly get headed. Racers will be very well aware of how to play these conditions to their advantage. This friction business has a role to play also in wind shear, because the wind nearer the ground not only backs, it also reduces in strength. Check the wind speed from your anemometer at the top of the mast by comparison with a handheld anemometer on deck. At deck level, the wind will be going slower and it will have backed. This is called wind shear. And finally, in local wind effects, we have katabatic winds and anabatic winds. Katabatic winds are downslope winds which occur when the mountain slope is colder than the surrounding air. They're also fueled by gravity. Sailing close to sheer cliffs, you can experience them as cold air falls off the top of the cliff. These winds are often called willy-waws. Famous katabatic winds are those that come off mountain ranges such as the Alps, where we have the Mistral and the Tramontana, or Eastern Europe, where we have the Bora and the Meltemi. Anabatic winds are upslope winds which are driven by warmer surface temperatures on a mountain slope than the surrounding area. The mountain slope is heated up by the sun and the air is sucked up the mountain. Now, fog. This is described in the weather forecast as very poor visibility and is defined as visibility of less than 1,000 metres. All fog is caused by warm, moist air over a cold surface. The cold surface condenses the vapour out of the warm, moist air to create cloud, or fog. There are a number of types of fog. We have radiation fog, valley fog, advection fog, upslope fog, evaporation fog, freezing fog, but we will concentrate on just two types, advection fog and radiation fog. In the case of advection fog, we have warm, moist air meeting a cold surface, in our case, the sea. We get this when the sea is cold in spring, for example. The air has heated up, but the sea has not yet started to warm up from its lowest winter temperatures, and there is a temperature difference. Or perhaps warm air from a warm front passes over the cool sea. The sea cools the air, and the moisture condenses out as cloud or fog. Advection, meaning the horizontal flow of wind or water. Advection fog can only be dispersed by wind. It cannot be burnt off by the sun, because if the sun beats down on the fog, so it heats the air up more and makes the temperature difference between the warm, moist air and the cool sea greater and increases the density of the fog. So an advection fog requires a wind to disperse it. The other type of fog we need to deal with is called radiation fog. Radiation fog occurs when the ground cools and radiates its heat and becomes colder than the air above it, and so the water vapour in the air condenses out as cloud or fog. This sort of fog can disperse with the sun. It'll burn off is an expression you hear. This often occurs in winter. To sum up, all fog is caused by warm, moist air over a cold surface. Advection fog, sea fog, requires a wind to disperse it, and radiation fog, land fog, can burn off as the sun heats the ground. Weather 3. The Beaufort Scale, the shipping forecast, what the terms mean, and the Maritime Safety Information Broadcast. The Beaufort Scale. It was in 1805 that Admiral Francis Beaufort, tired of sailors telling him it was blowing old boots out there, decided to compile a scale. After all, one man's blowing old boots was another man's light puff. The scale runs from force 0 for a wind of 0 to 1 knot up to force 12, which is hurricane force, with winds in excess of 64 knots, and for which there are 5 levels. You'll have heard the term level 3 or level 4 hurricane, for example. This scale was then further refined to include wave heights and sea and land conditions. Knowing what wind strength we will experience when we go out there is very important. Motorboaters really don't want any wind at all, so that the sea will be flat. Sailors need enough wind to get the boat going, but then not so much that it becomes something of a trial. And sailors need to be aware of when to reduce sail as the wind strengthens. It's just like changing gear on a car. We always like to sail upright, and so we set the sails to match the wind so that we achieve this. In terms of the forecast, winds that sailors will generally enjoy will be between force 3, a gentle breeze at 7 to 10 knots, and force 5, a fresh breeze at 17 to 21 knots. It starts getting a bit more exciting from force 6 onwards, with between 22 and 27 knots of wind, and force 6, a strong breeze, is the point at which the shipping forecast will issue a strong wind warning. Next up, from force 6, we have force 7, which is a near gale, then a gale at force 8, a severe gale at force 9, a storm at force 10, a violent storm at force 11, and then at force 12, hurricane force. Remember, when it comes to wind strength, that the forecast is giving you the true wind speed. That is to say, the wind speed you would experience if you were standing still, like at 1. If you start moving towards the wind, like at 2, then you will increase the speed. You will have your speed over the ground plus the true wind speed. And if you move away from the wind, or with the wind, like at 3, you will reduce the wind speed you experience, as you will have the true wind speed less your speed over the ground. The wind you experience each time is called the apparent wind. Now, if you can hear this, you're about to listen to the shipping forecast at midnight 45. That's 1:45 in the morning. It always reminds me that I'm staying up late. It's very evocative. I love it. You will get gale warnings followed by the general synopsis, and then you will get the area forecasts. And they're giving you the wind direction and strength and the changes during the forecast, then the weather, the sea state, and then the visibility.
Now here's the shipping forecast issued by the Met Office on behalf of the Maritime and Coast Guard Agency at 05:05 on Friday the 14th of January. There are warnings of gales in Shannon, Rockland...
With all forecasts, it's important to note what period the forecast covers, not just the time it was compiled or the time you're hearing it. This is particularly important when it comes to timings and when events will happen. First of all, they will tell you how fast the fronts are moving. Then most crucially, they will tell you when events will happen. So if you're given a strong wind warning that's imminent, that means you will experience a force 6 wind within 6 hours of the start of the period of the forecast. So if you're listening at 10:30 in the morning to a forecast for the period 0600 for the next 24 hours, and you hear strong wind warning imminent, then it may already be with you. If not, it soon will be. So what are they telling us? Wind direction and strength, that's pretty straightforward. We've just been through the Beaufort scale. Wind is described as where it's coming from, of course. And then a wind that backs is one that's moving anti-clockwise round the compass. A north wind, which moves into the northwest, is a wind that's backed. A north wind that's moved into the northeast is one that's veered. Weather can be described as fair, overcast, showers, rain, heavy rain. The sea state can be calm, smooth, slight, moderate, rough, or very rough. Actually, it can also be high, very high, and phenomenal. But you would hope to be hearing this at home from the comfort of an armchair and not out on the high seas. Visibility is described as good, 5 or more miles, moderate, 2 to 5 miles, poor, 1,000 metres to 2 nautical miles, and very poor, less than 1,000 metres. This is the definition of fog. Pressure tendency is measured within a 3-hour period and referred to as follows. The fact is that a change of 6 millibars up or down within 3 hours indicates a wind of force 6. Now rising or now falling denotes that while pressure had been, say, falling during the last 3 hours, it is now rising. And if it had been rising, then now it is falling. Now, the Maritime Safety Information Broadcast. This gives us a general synopsis and then the inshore shipping forecast. It's broadcast on VHF radio every 3 hours. The Coast Guard sends out a digital safety announcement on MMSI, which sets everyone's radio to channel 16. Then he announces on channel 16 that he will give his Maritime Safety and Information broadcast and which channel, 62, 63 or 64, this will be on for your area. Then on the selected channel he will give you a general synopsis and then the area forecasts.
All stations, this is Solent Coast Guard, Solent Coast Guard, Solent Coast Guard. Here's Maritime Safety and Weather Information broadcast.
For me, in the handle, it's the Selseybill to Lyme Regis forecast that I want.
Selseybill to Lyme Regis, strong wind warning in force.
So how does weather affect us? Here are a few pointers. The greater the distance the wind has to blow over the water, the greater effect it has on the water, increasing wave height. This distance is known as the fetch. Then wind against tide, or wind over tide as we call it, will create short, steep seas. Wind with tide, going in the same direction, the wind will flatten the water out. A swell can be caused by wind blowing for some time, or indeed wind from some distance away blowing and pushing the water along. This is one of the signs of a depression on the way, when you experience a swell for no good reason. Depth of water affects the sea state. Shallow water creates breaking waves, like the beach. Wind blowing off the land will be stronger offshore than inshore. Your heading in relation to the wind. Sailing to windward for a given true wind strength, the apparent wind will be stronger than if you were sailing downwind. Remember, always reef early and never put to sea without a weather forecast. There are a number of weather books available, but the one that stands out for me is the excellent Instant Weather Forecasting by Alan Watts. This is a book of some 24 pictures of the sky. You find a picture that matches the sky you have, look at the pressure tendency, and then it tells you what will happen. You know it's good when one of the most famous sailors of our time, Bernard Moitessier, recommends it. I'll leave you with a poem from A. A. Milne. No one can tell me, nobody knows, where the wind comes from, where the wind blows. It's flying from somewhere as fast as it can. I couldn't keep up with it, not if I ran. But if I stopped holding the string of my kite, it would blow with the wind for a day and a night. And then when I found it, wherever it blew, I should know that the wind had been going there too. So then I could tell them where the wind blows. But where the wind comes from, nobody knows. But then, of course, we do.